Welcome to my ACCU 2022 talk, What Classes We Design and How. And for those who watch this live, I understand if you are torn between the many other splendid talks right now in parallel, but I hope you can take for those who are not right now here, that they take the chance to watch it online afterwards. The slides will be are currently already available, and I'll show you in a moment. And I think it's 1 minute past, so let's get started. What classes we design and how. I'm Peter Sommerlad. And now let me get the focus on my. And if you're really eager to follow with the slides or download them, this is the QR code for the slides. And you can, if you have questions, you can either reach me on Twitter with my handle or send me an email. I don't mind getting bothered. If you don't get an answer within a week or two, then you might nag me again on Twitter if you have questions. For those who don't know me, I was a professor for software engineering, but now I'm working as a freelance trainer and consultant on C++, doing code reviews, caring about safety-critical C++ by working on the Missouri C++ guidelines, who I talked about last year at ACCU, and we will and some of the things that I learned from that is what I try to present here and give you guidance on. Now, one thing that I borrowed from Kevin Haney is that less code is more software. So whenever you are recognizing that you write a lot of boilerplate code, or let's say, do it this way because it has been done always this way without questioning what you're doing, that is where you should stand back and think, can I do it simpler with less code? Many years ago, we ran a workshop on simplicity in software with Giovanni Gasproni at ACCU, and this is still the motto, less code usually gives us more software. Now, to get started, I looked at C++ code and a lot of class designs and things that I did and that I read about and where I did code reviews. And then I was leaning back, so many rules about, we have thick books on guidelines and things that are recommended practices and things that are not recommended practices. And sometimes they contradict each other. And I wanted to know, well, what actually are the types or kind of types that we create in C++ or use in C++? And I came up with kind of what are the underlying roles, objects, or C++ types or C++ values actually play in a program? And does this categorization help us if we can find a good categorization, especially with the goal of getting to know how to handle values of these types and how to actually create the corresponding class types well enough so that they work good. And when looking at the things that are just working right out of the box are those types that have value semantics, so that represent values. And what a value is, we will see soon. So the good thing about values is that you can't do anything wrong with them in C++. The program that when you program with values, things just work right out of the box without any special incantations, without any special additional magic code that makes things work. It's just working, and usually as you expect. Then there are the situations where you not only have values that you compute with, but also you have things that you refer to somehow. And one reason you want to refer to something is because you want to have dynamic polymorphism, which is the object-oriented part of C++ that was making it popular in the 1990s. And I deliberately don't call these things objects because it's such an overloaded term. For example, you might know object from object-oriented programming, or you might know object from the C++ standard, where it actually means there is some memory where there is a value of a type in C++, and therefore I use the term subject here. And we will see what a subject is a little bit more in a couple of minutes. And then there are types that represent relations to subjects. So where the C++ object or the value itself is not self-contained, but relies on the existence of another value, and where actually the location of that other value is what the relation is actually containing. And there are several things of the relations, and I will give you more information on that, especially when it's safe to use relation types and why not later on. And then there's something very C++ specific. One of the killer features of C++ is its deterministic lifetime deterministic object lifetime model, where you know when something is actually killed or goes away, even if you don't pay attention and still have a relation lingering, but you know when objects go away, and actually objects can do cleanup code. When they go away, they can have a destructor. And all objects that actually have to define a destructor and do something with it are what I call manager types. And these are C++ specific. Many other languages don't have this. They might have garbage collection, but usually they don't have a deterministic point in time where you can do a good cleanup. Sometimes the languages try to get around with that and try to steal ideas from C++, but C++ is the only one that, or is one of the ones that introduced that concept and made it popular. And manager types are the cornerstone to have reliable and safe C++ code. Now let's look into these different roles separately, and let's start with values. And what is a value? There's Michael Jackson, which is not the deceased pop singer, but actually a Brit who wrote books on structured analysis and design. And he claims that that a value is something that is intangible, individual, so something that has kind of individuality and that exists outside of time and space and is not subject to change. So a value just is. And there are others, or let's say, what are values? And if you look at Scott Meyers, he says, okay, when you design a type, when in doubt, do just as the ints do. Actually, there are some things, the ints do, that are not automatically done by class types, but most of the things are just fine. There are a few things the ints do, especially the type int in C++, that you don't want to have in your own types, like the implicit conversions that ints participate in, but otherwise it's kind of typical what you do. And if you look at what does it mean outside time and space, well, a value can have different representation, but it's still the same value. In C++, we have that with the integer values. We can write in the integer 42 as decimal with 4 and 2, as octal with 052, or as a binary number, or as a hexadecimal number. All represent this same underlying concept, the integer of the value 42. And the actual behavior of these values is given by the operations defined on them, but it's independent of the how they are represented and what they where they are located. It's irrelevant. If I increment 40 or add 1 to 42, I get 43, regardless how that 42 was spelled or where it is actually stored. And the important thing, a value object is actually independent of other objects that are not contained within the value. And this makes it interesting because you can copy the value or give it as a value parameter to a function or return it from a function without the need to think about object lifetimes, validity of relationships, and so on. It's just the value. And this is what kind of functional programming is about. It's all about passing around values, and in C++ even functions act as values, or function objects can act as values. Whenever you call an algorithm pass a lambda, you pass the lambda more or less by value and let it go on. And in addition to being a value, there's also value semantics in C++. So all value types have value semantics in C++, but there are types that have value semantics that aren't values. Nevertheless, what does value semantics mean? Value semantics means in C++ you can pass a type by value, and if you copy a type with value semantics, the copy and the original have the same behavior, and the original remains unchanged through the copy. So that's, for example, where the old auto pointer that was trying to be unique pointer but isn't was wrong. If you copied an auto pointer, actually what you did, you changed the original and had a transfer of ownership of the underlying object referred by the auto pointer, which is not a nice behavior. At least it's not value semantics. And all of the out-of-the-box mechanics of C++ support value semantics. So if you don't do anything special, for example, if you combine types with value semantics in a class as members, that class implicitly has value semantics, so you can copy the types. And all the built-in types have value semantics as well. And there are a few cases where you can construct a type with the built-in mechanisms where you don't get value semantics. There are even some types that have something in the name. For example, if you have a shared pointer, which is a manager type, if you have a shared pointer to a const type, then actually using that shared pointer incurs value semantics, because the original cannot change, and so the actual object referred by the shared pointer gives you value semantics. So immutability can lead to value semantics. That's one of the means to get value semantics for big objects that you don't want to actually copy around. And there are other people like Joan Bolivar, who has a library on large objects that can have value semantics. On the other hand, if you add const to data members, is usually not a good idea. It gets you all kind of trouble and actually prohibits value semantics because it makes your type no longer assignable. And this is something you usually want to have your variables of that type be able to do. Now, since everything out of the box works in favor of value semantics and value types, I stop explaining them here and go for the more interesting types. So the next thing is subject. So what's a subject? A subject can actually play different roles, and it can actually be a variable of value type can become a subject once you form a reference to it. And what is important with the subject, I already told you, I have chosen subject over the object. The subject is something you pin down somewhere and you can actually refer to it, point to it if you insist on pointers, but there the identity is important. So it's no longer ephemeral as a value itself might be. Once you put it in a variable and refer to that variable by other means, then that object or that variable actually became a subject. So everything where the identity is important is something where you have a subject, and where the lifetime is also important, you have a subject. And why is a lifetime important? Because you form or you make something a subject by creating a reference or a relationship object to it. So you have something that refers to it, and that other something needs to know how long that subject lives to understand how long it itself stays valid. And one means where we use subject is actually when we want employ dynamic polymorphism in C++, when you have a reference to a base class or a base class type, and then have behind that references instances of subtypes of the base type, and thus can have polymorphic behavior. So something becomes, or a C++ object becomes a subject once a relation is actually formed to it. So for polymorphic subject types, they let's say, dynamic polymorphism relies on being actually a subject because it relies on pointers or reference being passed around using the base class type and to actually referring to subclass object. And if you want to have dynamic polymorphism, there are a few things. If you create a class type preparing for a polymorphic hierarchy in that base class type, you will have virtual member functions, and you have to define, or at least, you have to define a virtual destructor or declare it at least, so that heap allocation that is referred to a base class pointer is actually cleaned up properly. And what you also want to do is you want to prevent copying. So you want to eliminate value semantics from your base class type to prevent object slicing so that you not accidentally create a base class object from a subclass type by, instead of passing on the reference, passing on a copy, and the copy slices to the base class type. And there are other means to get dynamic polymorphism. There are nice talks by Sean Parent, who explains deeply how to create dynamic polymorphism by putting the virtual keyword in a box and just have types with value semantics, which can be a great relief in the ease of programming and lifetime management. But that's something I don't show today. Now, we talked about subjects very briefly and the problem with dynamic polymorphic types. And then let's look what makes a C++ object a subject. This is done by forming a relation to it. And this is something that is interesting because some relation types we see very obvious in C++ code. So, for example, forming a plain pointer or forming a reference is actually creating a relation to a subject. But other types exist that are relation types that are not so obvious, and they have value semantics, and so they easily can be returned from a function, and that is where a danger is lurking. So what's a relation? It's actually a link or reference to another object, which becomes a subject. So it uses the identity of some other object to refer to that other object. And it enables something that I term with the German word Fernwirkung. It allows us to remotely drag a remote subject into an expression where it actually is not participating directly by referring to it. And this is what I call Fernwirkung, because remote is so overloaded term that it's kind of hard to grasp what I mean by that. That's why I termed that Fernwirkung. And it enables us to having these relation things to get dynamic polymorphism in C++ style, but it enables also the use of of non-copyable objects and of things that are very large and where we want to optimize away the copying that might create an overhead. Now, what is Fernwirkung? It allows us to access or modify an object that is not directly a participant in the current expression. And usually we use that by employing references, especially reference parameters. We can have a const reference parameter, which acts almost like a value parameter, except that it optimizes away copying. We have regular L value reference parameters that allow us to have explicit Fernwirkung on an object, so have a side effect on a parameter. And then we have the transfer of ownership parameters that we can form by using an R value reference, which is kind of expert level territory if you write library code. But there are also pointers, which are similar to the L value references, but we have types like the class span in C++20 or other view types or iterators or string view, which all have these Fernwirkung effect and especially have the potential to actually dangle, which is part of the technicalities of a relation type. It relies a relation object, a relation C++ object, or a relation type value is only valid when its original is valid. So it has the danger of becoming invalid or being invalid from the start, which means it's either dangling, or in the case of pointers, you can have a null pointer, so that it means it's empty. So you have to take care. The good thing about emptiness, it's usually detectable. The bad thing about emptiness, you have to program around it in your code. On the other hand, if something is dangling, that is when you have to employ address sanitizer to figure out your bugs, but it usually means that you access something that is already dead in the term of the C++ lifetime model, and that's really, really a bad situation because it is undefined behavior, and as you know, anything can happen. And inspired by Tony van Aert, I usually name those types that can be potentially dangling dangs, because it's very easy to make them go bang and explode your code. And why do I make so much fuss about these relation types? Because this is the area in C++ where you still need our superhero capes and masks to actually track the lifetime of other objects and make sure that we don't get into the dangs situation. And there's one case where it's safe to use relation types. It's as function parameters, as long as this function is not a thread function starting a thread or a coroutine where dangs are really going boom. There are the built-in relation types, or those that you can create. We already said that by forming reference or pointers, and there are all these kind of iterators, spans, and views. And the interesting fact is when you have a data member of your class type that is of relation type, it makes your class a relation type as well, unless you actually make your class a managing type. So it's kind of contagious, a bit like the coronavirus. So relation types are contagious, but you can do something about it. And I would say all managers will have a data member that actually is of a relation type, because it refers to the resource that's somehow outside of the managed object, and the manager gives it more properties and ensures that you don't get into the situation that the users of the managers get the problem of a dang. Now, again, using relation types, this is where you need your superhero cape. Parameters with are the safe area of the relation types. There's usually no dangling property possible. I said that. And where you actually have to be very careful is returning a relation type. And that requires the caller to be very careful what to do with the relation. If you return a reference, the caller might just store it in a variable by creating a copy from the reference, which is a safe operation. But if you just keep the reference around, that's really, really dangerous. If you use the expression that returns a reference as another parameter to a function call, that's still the same full expression, so that's still safe. But it can also be safe from if you return a reference to the guts of an object from a member function, but then you must ensure that the member function is not callable on a temporary object, because that can be very dangerous. And even the C++ standard definition in the core language and the standard library suffer from cases where they return references to the this object or parts of the this object, and these member functions are callable on temporary objects. And if you keep the reference returned around, you have immediately dangling in case you actually call that on a temporary object. And so if you want to write safe code and don't want to leave your narrow lycra suit at home because it doesn't fit well enough over your belly or hips, then it's better to actually never keep a returned reference or relation type that includes string views and spans as a value in a local variable or in a variable, and use it later because it might be dangling when you use it. One example, this is the definition of a very simple function, and I believe it's even almost like it is defined for the standard library, the maximum of two values, and to optimize the parameter passing. The parameters are defined by const reference, and it's assumed to safe to return the const reference because it's already passed from the parameter. It actually fails. Interestingly, like we see below, once we start memorizing the result as a const reference, and this is actually pretending to extend the lifetime of the result of a temporary created here. The problem is that function call doesn't create a temporary. The temporaries are created as parameters of the function calls to string objects. And what you actually, and these string objects, because they are parameters, are destroyed before that X can be used. So they are destroyed at latest at the semicolon of that declaration statement. And that means they are destroyed whenever you use X, the string it refers to, it's already destroyed. And that is when your program is just wrong. So the best thing is never try to, you might see in, let's say, pseudo clever code, a lot of cases where either R value auto refref or some other auto constref or some other constref or refref local references are created with the intention to get lifetime extension and safe copying. C++ 17 gave us a lot of places where there's mandatory copy elision. So all these clever codes are no longer really in optimization, and they're actually a very big foot gun, the size of a tank sometimes. So don't do that. Everything that's pink in my slides, regardless where you look, is usually very, very bad code. Now, another example that is borrowed from Nico Yusutis. Just consider we have a lambda that returns a vector of strings very happily by creating that from whatever. And the trick is vector has a member function called add. And if you call that member function, it will happily work on a temporary object and return an L value reference to that object. And I can actually store that L value reference. And again, like in my previous example, and I forgot to color that pink, so this is also very bad code because this reference S immediately dangles. And if you run that program, which I think I can show you, it actually, let's make this a little bit bigger. So this is a program that we just seen. And if you make this S also a bit bigger, we can see that it's happily outputs hello world, and we can even change the string and it is hello world. So everything seems to be fine. Well, until we actually turn on address sanitizer. And if you look at the same program and let it run, and we see that address sanitizer warns us, okay, you've done something very, very badly because you had a use after free, and that is not very nice of you to do things like that. But do you run everything, every piece of code through address sanitizer, and have you test case that actually will trigger it? That's really, really something to take home from. So never, never, ever do things like that unless you actually know and have the actual address sanitization in your build system to actually check that you don't do it wrong. And I have some optional slides, and I think we have enough time to actually show that, to give you a visual presentation of how to use relation types well enough. And remember, it's not only references and non-owning pointers, it's also spans and views and all kinds of things that contain these things. So everything is fine when you have, if you look at your call tree and pass something, a relation object down the call tree as a function argument, and you might even, if you refer to that, it actually has this kind of this dashed line is actually the Fernwirkung line where you refer to it and look it. And it's good to memorize relation types, actually parameter types. Use them as parameters. That is a safe way, and that's where they are used either to enable the Fernwirkung by having the mutability of the original, or by enabling the copy optimization with const references without having the need to copy stuff around. And that's it. Other uses, for example, if you use a global variable where you have a Fernwirkung by naming the global variable, that's really bad code. Why is it bad code? Because it makes your code untestable. So global variables actually are a killer to testability, and you don't want to do that. They cannot dangle because they stick around. Well, there are some corner cases in C++ where they can dangle, and there are even misra C++ rules that tell you when those happen. The keyword is dynamic initialization of global variables, and there's a whole industry of patterns that have been created around that, like the original singleton pattern, which is also not a good idea to use. And so, because it hinders testability, and you want to have good testability, especially to use address sanitizer to find your use after free bugs. What you can use actually, if you need to use global variables, and there are some environments, for example, an embedded system where you don't want to spend heap memory, but you still want to keep stuff around, pass them from main. For example, I teach C++ in a way that you use the global variables standard C in and standard C out only in the main function to pass them down the call chain to your function that use the IO stream or iStream or OStream references as parameter types. And then you can actually write test cases for your functions and never use standard C in and C out directly in your code except the main function. And this is somehow safe, because you still get things just as a parameter type, and the Fernwirkung just happens to go to the global object, but it could also go to something else, and this makes your code actually testable. So whenever you see in your function code that uses standard C in or standard C out directly, and that's not the main function, consider refactoring it and introduce the OStream or iStream reference parameter and make your code testable and start the opportunity to write test cases for it. If you return a relation type, like a reference, a pointer, or something else, especially to a local variable, like a string new to a local string, that's not a good idea because you get immediate dangling. And the bad thing is your code might just work, just have undefined behavior. And as you have seen in my example in Godbolt before, the code still works because the bits are still somewhere in memory, even though that memory no longer has a valid C++ object in it. So never return things badly. It might work if you return a reference, a relation that you just get passed down in the same expression that created the underlying object, and don't rely on lifetime extension because it usually fails, especially it fails easily when you refactor the code, and the rules for actual lifetime expansion extension are really, really tricky, and very few people can actually cite from the top of the head if that reference that you captured locally is actually keeping things alive or not. And it's really, really tricky. And a naive refactoring can make code that work because lifetime extension was happening to code that doesn't work, and you by a maintenance program and without address sanitizer and thorough testing, you will not recognize that bug. So it can work, but keep your superhero abilities aware to get that. Now, never pass relations to threads unless maybe it's a relation to an object with a mutex, where you can guarantee that the lifetime of the mutex and the protected object is actually longer than the thread lives, and all the accesses are to proper synchronization mechanisms. If you pass an unsynchronized, just a reference to a thread object that is, let's say, data race is almost guaranteed or very easy to get to, and that means you will have the problems in your code, and that is undefined behavior. So be very careful with threads, and this includes coroutines, because also with coroutines you might have synchronization problems, because you might not know if a coroutine is actually continued on another thread, for example. So be careful. Globals and threads are also dangerous. Even if you pass them, they cannot dangle, but they can still have data races. And there is only very few situations where you can have sharing of globals, or let's say long-lived things. That's when those are actually atomics or mutexes, or stuff that is properly protected with the mutexes, where you can actually ensure that the lifetime is longer than all threads that might use it, and where all accesses are properly synchronized, but still that requires our superhero abilities. Now, let's get to the beef of managers. I think that was one of my big revelations to actually what makes a manager and what kind of managers are there. And I hope others will pick that up in the Misra C++ group. I already, let's say, had my peers brainwave aligned that then I talk about manager types and the different things. And I hope in the future, all C++ people will get their head around of what managers are and use them very consciously and actually create them consciously, which is the more important thing if you create these types. Now, what is a manager? A manager type handles a single resource. If you need to manage more than a single resource, combine manager types in your class types of appropriate category, and then it still works. And that's the power of C++. But never attempt to have a manager, or let's say, don't be naive when you attempt to have a manager type that manages multiple resources, because it's very easy to mess things up and very hard to get it right, especially if you consider exception safety and resource leak safety. It's really, really hard. I tried it once with unique resource as a standard proposed type. It's available in the standard library. Technical report, which is a potential extension of the standard library, but it never made it into standard. I think it's good it never made it in the standard as of today. But I learned a lot on how to write actually manager types. There are three kinds of what kind of managers we create. There are managers that are very easy to create, scope managers, where you just care about having the scope-based resource management, or RAII, where you acquire a resource in the constructor and release a resource in the destructor and make sure it's not falsely shared, and that's nice. And clean, and there are a bit more sophisticated managers, which I call unique managers, which guarantee that you can transfer the ownership of a resource, where it can no longer be duplicated, which might help with multi-threading or other situations where you transfer the ownership. It's a little bit like what Rust is doing with the borrowing there. And you might know it from unique pointer, that unique managing or unique lock. And then there are the types that are general managers, which actually care about copying and resource duplication. And they actually manage resources in a way that they become value types so that you can actually safely use them without thinking a lot about these types. And examples are standard string and standard vector, all these standard containers that you just can use and they just work. So how do you recognize a manager when you don't know if a class is a manager? Every class that defines a non-empty destructor is actually a manager type because there is something cleanup happening. And they usually, I would say, they usually have a member of a relation type. Sometimes that relation type is a value type that is actually a relation type in disguise. For example, if you have a class for handling operating resources like files, you might have a file handle that in POSIX is represented by an integer, and that file handle is actually a relation type to a resource, where the resource is actually something in the managed by the operating system, identified by that integer. And this is where, let's say, it's not a programming language relation type, but a relation type in the semantical sense. Other things, examples might be a row ID for a database, where you refer to a database entry, for example. And managers need to care about copying or moving because the built-in mechanics of the language, like the compiler-provided copy constructors and copy assignment and move constructors and move assignment, may just do the wrong thing and may cause a duplicate release of a resource, or may cause typically duplicate release of a resource. So that's why manager types have to care about copying and moving. And this is more or less where Scott Meyers' rule of 3, original for C++ 98, was actually referring to. Once you care about copying and moving, you care about destroying the object, or when you care about destroying the object, you have to care about copy operations. Because in C++ 98, we didn't have the move operations yet. Now, what can you learn about that? Because defining a destructor makes a class interesting, never define a class with an empty destructor, with an empty body, because that is code. Remember, less code is more software. That's code that is worthless. And it can be confusing. And it's also pessimizing your code, your class type, because it prohibits the generation of the compiler-provided move operations, which might just work. For example, the Mars drone, the helicopter, I looked at that open source code, and this code base has a lot of classes with empty destructors defined, which is really, really not a good style and not good. So when you go home tomorrow or on Monday and look at your old code, look for classes that define empty destructors and just delete them. So don't define class with destructors in an empty body. There are very few exceptional cases, not to the empty body, but where you manage something that is not obviously a resource. But most examples I have seen, they have some global state that they manage, and you can consider that global state actually a resource that you manage if you squeeze your eyes right. It's maybe not an obvious thing to have, like things where you have object counters in your class or something like that, where you care about copying and so on and deletion. But it's still a managed type because you manage that global counter. Now again, how do we implement these different styles of types? We have the scope managers, which are non-copyable and non-movable, and that's very easy to achieve. And from C++ 17 on, scope managers are very often sufficient because we can return them from a factory function because of the mandatory copy elision if you construct them in the return statement. And this makes it quite safe to use and sufficient, and you don't have to get into shenanigans that are required for transferring the ownership or even duplicating the resource that you would do with the general manager. Now, why did I come up with that model of value types, subject types, relation types, and manager types? These roles of the types and sub-objects and even of base types and members influence what your own class types actually are. And defining a class type correctly can be overwhelming. Just consider Nico Yusudi's book with, I think it's almost 200 pages just on move semantics. And that's just 2 of the 5 special member functions that you have to care about. And it's really overwhelming, and having a mental model around these categories of types that you create is, I think, a big help in defining your class types correctly. I'm sure if the authors of that mass drone software would have known about this categorization and would have consciously created the types, they would never have gotten the idea of having class types with empty destructors. And if you just look at it naively, we have these 5 special member functions. We have the destructor that we might need to care about it. We have the copy constructor. We have the copy assignment operator. And to actually make it safe, because the compiler provided one is actually allows you to copy, call it on a temporary, create a reference as its return value, an L value reference to a temporary object. And if you capture that L value reference to the temporary object and use it later on after the temporary has gone out of scope, you're in a big trouble, because what you get is actually a reference to that object, and that causes immediate dangling. And to ensure that your copy assignment, if you ever define it, is not callable on a temporary object and not giving you a dangling reference, it's best to actually mark your copy assignment operator ref qualified, and this prohibits using it on the left-hand side with a temporary object. And similarly for the move constructor and the move operation, and to actually make use of move operations, always or only define them when you can define them as no except operations, because only then they are safely used by the standard library to optimize the move. Otherwise, it's usually not a good idea, and they won't be used automatically or can cause resource leaks in some very strange situations if they are not no except. And sometimes it's better to not mark them no except and just provide the copy operation in your general manager types to just make sure, because it's can be simpler. In addition that we have these 5 things, we can all of these 5 can be either be public, protected, or private. Most of these not defining them public is ridiculous, but in theory, you have these 3 options, and then you can either have them not declared, which is a good thing because the compiler provides them for you. We can explicitly define it as equals default, or we can declare them as deleted, or we can define them with a non-empty body and do something useful for it. And if you combine those few options without different with just the canonical spellings of these operations, you end up with at least 50 different possibilities, and that's really overwhelming, even if many of those don't make any sense, and there are more that might make sense in very special situations, but are usually not, let's say, wise to use. Now, this is a lot of confusion, and there are just a few cases that actually make sense. And Howard Hinton in 2014 gave a nice ACCU talk where he created this table and developed it over the course of 90 minutes, and even showed that the standard is buggy with respect because of legacy. So we get copy operations when we define either of these three that should always be defined together, and that is more or less the cause for the rule of three by Scott Meyers. And there are also interesting cases that when you define a move operation, you don't get the copy operation, which is something I want to make you aware of, because that will actually be helpful to get your code to write less code. Now, if you look at the sub-object influence, once we combine value objects, everything is fine, nothing bad can happen. That's why you should fall in love with value objects and values, let's say value objects, not only value semantics, but value objects that just work independently of all the other things surrounding your program. Relation objects, they're either contagious if you have a sub-object that is of relation type category, or make it a manager, which is the more often useful thing. When you have a polymorphic, defining a polymorphic base class intentionally, make sure, or let's say, everything is fine if the base class is well defined, and I'll show you in a moment what that means. And if you have a scope manager and make this a member function, your surrounding class becomes a scope manager, and that's okay. For example, if you want to manage multiple resources together, just combine different scope managers in your class, and your class becomes a scope manager. Similarly, with unique managers, if you combine multiple unique managers, it's still okay because the compiler provided operations just work, and the individual unique managers guarantee no resource leaks. And again, general managers, they behave like values, they have value semantics, and so they are just fine, like in the top level. Now, how can we define a class? Remember, less code is more software. So the easiest thing is let the compiler do its job and provide the special member functions for you. And this is what the rule of zero is about. And I told you what the sub objects of your type actually have an influence, but it's just rely on the rule of zero, unless you must do something different. And there are only four cases where you must do something different from the rule of zero. And what are those? And what I think the core guidelines say use the rule of zero, but they have a very weak rationale. They say, oh, it's the simplest and gives the cleanest semantics. What does it say? It's the simplest, so it can be wrong. And they don't tell me when it's wrong. So what is my take? Okay, implement your class in a way that the compiler provides different implementation does work. And I'll tell you in a moment when it doesn't work. And refrain, some people say, oh no, we always define everything with equals default. Don't. It can be a pessimization, actually. And it can change overload resolution. It can make your code bigger. At least it makes your source code bigger. And it changes sometimes the ABI because some compilers can pass aggregate types with trivial members as directly, and sometimes you might end up with losing the ability that something is an aggregate. I think that changed again with C++20, but there are some cases, if I remember correctly, where just defining the copy and move operation and the structure as equals default changed the thing that the class no longer is an aggregate. Or let's say, might change the compiler's treating of that class type. And there's one exception, or actually two exceptions for equals default. One is that you want to resurrect the default constructor after you have defined another constructor and the default constructor just is correct. The default is default constructor. And the other case for equals default is for the virtual destructor in the polymorphic base class, where you define it not with an empty body, because I told you that's a bad thing to do, by defining the virtual destructor as equals default and in the polymorphic base class. So when is the rule of zero ill-suited? And it's then bad when you actually, a class needs to define a destructor, either because it's a polymorphic base class or because it's a manager class. And it's the reason for the non-rule of zero classes. There are the exceptions where you have the resurrect the default constructor, and I have some small print on that slide, but I'm not sure if it's actually true, because I think you can just rely on manager types categories that I have things. So for polymorphic base classes, there's one case which could have actually be detected by a unique pointer, which is and make unique, which is the thing that we use for creating things on the heap, where we employ polymorphic types, but it isn't. It was actually proposed in the 2004 or 5 as a side note in another paper introducing other stuff, and it never materialized in the standard library. And because of ABI problems, we cannot actually change the default deleter to actually have that concept check on its class type, on its parameter type. So we wouldn't allow the derived to base conversion if the base type doesn't have a virtual destructor. And if you consider writing very safe C++ code, consider replacing your unique pointers default deleter with a deleter type that does this check. And to prevent slicing, you want to have these polymorphic base types actually to prevent copying and move operation, because you don't want to have slicing. The best thing to do is actually to wrap things in a type erasure in the box, in an envelope, like Sean Parent is showing us, but that's not the topic of today. So if you learned C++ in the ancient days, you learned, okay, to prevent copying, you can define or declare a private copy operation and don't define it. You can actually have a protected copy operation, so that can be employed by subclasses if you insist. Or what I taught later on is actually inherit from boost non-copyable to ensure that your class is non-copyable. In C++ 11, we got new options, so everybody jumped on that and told us, well, you delete the copy operations, and then everything is just fine, with the issue that because you delete or you define the copy constructor as deleted, you lose the ability of having a default compiler provided default constructor. So you actually have to resurrect your default constructor by defining it with equals default, additional code. And when I was thinking about that and looking at Howard's table, I thought, well, can we actually make that simpler by writing less code? That's even more obvious what we're doing, because equals delete and equals default look very, very similar. And if you have a quick glance at your code, even the compiler will perfectly understand what you're writing. It's quite easy for a human to either misread that or even mistype it from in your IDE when you mean the other one for the other. Now, if you look at Howard's table, there's this last line where we see when we define a move assignment operator, we don't get a move constructor. we don't get a copy assignment, we don't get a copy constructor, and still the default constructor is still there because we didn't define another constructor. And we still get a destructor, but the only case where we actually do something with the move assignment is actually when we have a user-defined destructor. And how do we make a class non-copyable? If the class type is T, we can actually define our move assignment operator as equals delete, and that's the least amount of code to prevent copy and move operations in your class type. And I nicknamed that some years ago at ACCU as the Rule of DesDeMovA. There was even a lightning talk on that. It's still contentional. You might find a better name, but that's how I call it right now. And this is what the simplest way to prevent copy and move operations of your class type by using the Rule of DesDeMovA. And for polymorphic base classes, so the generic thing is we have some base class type, we have a virtual member functions or more of those. We define our virtual destructor as equals default, and we prevent copying by defining our move assignment operator as equals delete, and that is the least amount of code, and that is my canonical form for polymorphic base classes. And if you come up with, oh, but, yes, there might be buts, but think if your buts in your code actually are good code or just accidental code pieces that you created in your base classes. Now let's look at the manager types, which are the more interesting things. Virtual is very overrated in modern C++, and even if you look at the standard library, there are very few cases where virtual were introduced in the past years. One is just the polymorphic memory resource, and most other data types actually just are templates or use virtual encapsulated, like, for example, standard any or standard function. Now, we know in C++, or we might learn in C++, the killer feature of the destructor, killing the object and cleaning up any resources managed, is for RAII, or scope-based resource management. And this is the case when you define the destructor body. And this should be the only case when you define the destructor body, that you clean up a resource that you acquired in a constructor. And the principle is the key canonical feature, and you need to care about copying and moving, and the three cases I cared, and don't try to manage multiple resources at once if you really want to know how to do that. And I needed help by Eric Niebler, and we tried to get that thing working, that unique resource. We both think it works, but I'm not sure it absolutely defeats all malicious code that is out there. Actually, you can look at the example implementation in the paper P52 and look at that if you're inclined to do so. Manage a single resource, as I said. Scope, unique, and general managers, and let's look at how we define that. This is a canonical example of how to define a scope manager. Typically, you will have a constructor that has actually constructor parameters, because when you acquire a resource, you usually would actually provide means to identify the resource that you want to acquire. And you will have additional member functions to actually wrap the resource and provide access to it. And you define a destructor that actually releases the resource, and this heavily depends on the resource, what code you would put there. And then we have the apply the rule of DesDeMovA by defining our move assignment operator as equal delete, and we are done with that. And that's it. And that's sufficient. If you want to pass access to the resource down the call chain, you would actually have functions that take that resource type by L-value reference, and then the called functions can make use of the resource via Fernwirkung, and still the local variable holding the scope managed resource is actually cleaning up in the end when the call stack is unbound and the code that defined the resource is left. Now, unique managers, this is where things become more interesting, and this is where we have a standard library type that helps us implementing it. You might have other options, but this is a canonical guidance on how to do that. Why do we need to manage the resource internally with a standard optional? It's because we need an empty state. A unique manager has the ability to pass on the ownership of the resource. And once you pass the ownership on, you no longer should refer to the resource, so that you can actually ensure that your destructor doesn't release the resource twice in the original and the transferred class. And this is where standard optional provides the correct semantics for you. You might use other things. For example, a unique pointer just uses the ability that the null pointer is a defined invalid pointer and can demonstrate the non-existence of a pointer to object as its default state. And that would actually be the implementation strategy of standard optional of an L-value reference type, which we don't have because of reasons which I don't want to repeat here. But whenever you are influencing C++ standardization, nag your national standard body to fight for getting standard optional L-value references, like all the other optional implementation by Cybrand or Anthony Williams or Boost provide. Now, what are these special member functions? So we factor out some code for releasing the resource because we need that from the assignment operator and the destructor. And actually, the default constructor can be default because the default optional would actually be an empty optional. And that's my suggestion is that default constructed state of a unique manager is the empty state, and this is a good thing. You should have a very, very good reasons to not make the default constructor create the moved from or the default empty state of a unique manager. I haven't found a case where doing otherwise makes sense. And if you have types that do otherwise, think about it. Now for you will have a constructor taking parameters, as I said before, identifying the resource that you want to acquire. You will have a destructor that releases the resource, and you will care about the move operations. And this is because you care about these three special member functions. This is why I call this a new rule of three for unique management, where you care about the move operations. Now, how do we implement that? It's a canonical example, so it actually gives you some information. So, for example, for the move constructor, we move the optional, which might move the underlying resource, but it keeps the other, let's say if the other resource if the resource type is not move only, it just copies the content of the optional. So we actually have to reset the right-hand side optional so that it becomes empty afterwards. So we have to clear it. There's no other thing we have to do with the move construction because we originally didn't exist. So that's sufficient to get there. And this is why for a unique manager, the defaulted move construction would be insufficient in its definition. Now for the move assignment operator, here ensure that you L-value qualify it, and we want to prevent self-assignment because that could actually empty a resource without knowing. So if we ensure that self-assignment is a no-op, this is a safeguard. There are people who say, oh no, we don't have to do that because code doing self-assignment is wrong anyway. I think I would like to err on the safe side and check for self-assignment in the assignment operator here. Because we actually release the resource, this is code, what goes in the release function that is application specific, resource specific. For example, you want to close a file or you want to delete some other resource or whatever you're doing. This is specific to the kind of resource and the acquisition and release of the resource. And then we swap the two optionals, which actually swap the resource, and swap is guaranteed to not throw. And therefore we mark this no except. And the release function actually checks the optional if it has content. So it is a no-op if it's empty, but if it's not empty, it actually needs to release the resource. That's code that you actually have to write, like close a file and so on. And you reset the optional to the empty state so that there's nothing bad that can happen with it, especially when you swap here in the move assignment. And for the destructor, it's just releasing the resource that's sufficient for that. Now, there are some purists that saying, oh, I reset the optional in the release of the resource. Remember, you usually handle with operating system resources where you make a system call to actually release the resource, and that's quite expensive. So resetting the optional superfluously is not a big thing, and the compiler might actually optimize it away because it will look through your code and actually see the reset if you implement everything in line and see that nothing bad should happen. Now we are all perfectly able to implement unique managers, so there's no need for unique resource as I proposed for the standardization. Now the big thing is general managers. The best case is you don't have to write your own general managers, but use the ones provided by the standard library like vector, string, or whatever container you're using there. But there are a few cases where you actually need to care about, and this is where you have to implement your own types that are general managers. And this is where you actually care about a destructor, you care about the copy operations, and you might want to optimize your general managers for transfer of ownership by implementing move operation. But this is a pure optimization. For unique managers, is part of the underlying semantics, the transfer of ownership. But for general managers, implementing move operations is for pure optimization, and it only makes sense when the copying is more expensive than transferring the ownership of the held resource. And what happens, this is my one-line explanation of move semantics. You have on the left-hand side a box that's empty, and on the right-hand side a box that has some content. And what does the move operation actually do? It moves the content to the left-hand side and keeps the right-hand side empty. And that is when you actually move. If you don't implement move, what happens is both boxes are full. The left-hand side box will contain a copy of what's in the right-hand side box. And it only makes sense when you have some envelope letter idiom where you have a box and something in there that you can move around and signify that the box is empty. And this is the classic rule of 3. You have a destructor and the copy operations, or you might think about the rule of 5, where you have the copy and move operations and the destructors being defined. And again, defining the move operation for general managers only makes sense as an optimization, as our, let's say, demigod Don Knuth told us. Premature optimization is the root of all evil. So only implement the move operations for your class types when you actually can prove that you get a benefit performance-wise that's relevant. less code is more software. So a general manager provides value semantics for a resource that doesn't have value semantics. It usually implies kind of expert level coding. It's kind of a library level language and explicit cleanup. And the resource must be copyable or replicable. Very often it doesn't make sense for a resource to be replicable easily, especially if it's operating system resource, so it's a cause for a unique manager or even just a scope manager. But general manager types can be helpful, and sometimes resources are easy to copy, like especially as you see in the central library, vector and string manage memory on the heap, and memory is one thing that's easy to copy. It might be expensive to copy, but it's still easy to copy. It's guaranteed to just work, given that the types in the memory are copyable. And it's very often much simpler and easier to just reuse existing general manager types and squeeze their semantics to your needs instead of implementing your own. Now I'm running towards the end, and there haven't been any questions so far, so I give you some chance in the end. So what are my takeaways from this talk for you? Consider roles of objects. Create non-value types only with consideration. And whenever you use a type, be consciously aware, is it a value type? Is it a relation type? Is it a subject where the relations that you create to it actually might outlive the subject, which is dangerous? Think of every iterator that you memorize, or every let's say reference that you create. Think if it outlives the actual subject, and derive from the value semantics only when needed for polymorphic base types, which should be rare in modern C++ or even encapsulated, or for creating scope and unique managers. And if you have other types that are neither, that don't have value semantics, think hard if they either fit one of these things or if they are somehow have a broken semantic model underneath. Handle relation objects with care, only pass them as function parameters, and especially be aware of them when they are disguised as class type, as the standard span or standard string view, or even ranges has a lot of them. They actually at least try to be safer by inheriting or providing that they are a borrowed range, so they won't actually show you that you shouldn't actually memorize them and not return them. Special member functions, the rule of zero rules. Rip out all that needless copy, defaulted operations or empty destructor bodies. Just eliminate the needless code. Never define a destructor with an empty body. Delete all those that you have. Equals default the virtual destructor in the base class and only there. It's rare for polymorphic hierarchies where the leaf classes might actually be also manager types. It can happen. For example, the IOStream library has this situation where the string stream or string buff and file buff are actually manager types managing the underlying resource, either memory or the open file. But it's really rare that the derived class actually needs to implement the destructor. And there are three kinds of managers. They apply the rule of DesDeMovA for the non-copyable types, the scope managers and the polymorphic base classes. Provide the rule of 3 for the move-only unique manager types, and the rule of 3 classic or the rule of 6 for the general managers if you can actually benefit from optimizing the move operations. And that is how I conclude. What is missing, I didn't show you what I referred to, how to encapsulate virtual and how to have runtime polymorphic types with value semantics. And this is what was classically called the envelope ladder pattern. You can either use variant if your limit of variation is fixed and the size of the different types is not too much difference, or you look at Sean Parent's talk, A Better Code, Runtime Polymorphism, where he elaboratively explores how to create polymorphic types that have value semantics by wrapping all usages of virtual in this envelope class that happens to just work with whatever you throw at it, as long as the required API is somehow fulfilled.